Okay, start recording. Oh, she's one more person. Okay, so yeah, let's start on the problems that nominated by the attendees. And so this is the problem that we're going to go through in extra. And there are 50 points on a chalkboard number from like 1 to 15. So basically you kind of just randomly put down 15 dots, if you just do that. And then how many lines can be drawn to connect every pair point whose sum is odd, assuming each line connects just one pair of the points. So basically, if you label it, it's 1, 2, 3, 4, and 5, 6, 7, 8, 9, 10, 11, and for example, if I just add 12, 13, 14, 15. So basically, if you just do this, and you will begin to try to make connection and trying to connect that sum is odd. So basically, you're trying to connect this works. And if I use a different color, for example, 2 and 4, that do not work. So this do not work. And like 1, 3 also do not work because they total up to be 4. Soon I will find that the only way to get sum is odd is 1 even and 1 odd. So basically, I have to, so basically, I had to choose an even point and I choose an odd point. Or if I choose odd point, choose even point, it does not matter because basically, if you add, because the line do not have direction. So basically, I just have to design steps. Step 1, odd, even. Step 2, odd. And to choose even point, an even point out of those number, I have 7 even numbers. So that's 7. Cardinality is 7. And this one is odd is 8. So 7 multiply 8. That's the way that you can get a pair. And we don't have to multiply 2 or divide 2 because it's already the final answer. So this is the first problem. The second problem is that if for the pick of 3 lottery, so pick 3 lottery is the name of one type of the lottery they have. 6 balls number 1 through 6, 1, 2, 3, 4, 5, 6 are placed in a hopper and randomly select one at a time without replacement to create a 3-digit number. So basically, a hopper is like this, and you get kind of just got 6 balls rolling, and when it's settled down at the bottom, it's going to extract a ball out. And without replacement means that you're going to take one away, then take the second away, then take the third away. So basically, each step. So you can build so for the counting and statistic problem, the key thing is to build a step which will end up with the end result. Keep your eye on the end result. End result is a 3-digit number sequence. So basically, and we focus on how this sequence is built. For example, if I step end result, for example, could be a 3-digit number. 3-digit number, obviously, they care about this, order of the number. So for example, if you draw 6, 5, 4 is different from 4, 5, 6. So basically, in this case, the step one obviously is pick the first ball. We have a full spectrum of from 1 to 6, so that's 6. Then under step 2, obviously, you know, we are given like 5 ball to select from, so we have to multiply 5. And step 3, we actually has 4, so but 6 multiply 5 multiply 4. So that is also like 6 permutate 3, means that, you know, I'm trying to permute 3 number out of 6 total. So basically, it's actually also equal to 6 factorial divided by like 6 multiply 3 factorial. So basically, you know, that's the formula for the permutation. So if you calculate it, that's kind of 20 multiply 6 equal to 120. So that's the end result for this problem. And then let's go to this problem. And so in this problem, we are talking about a parking lot, a nice spot parking lot. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And if principal always get to one of the 3 shaded spots, let's say that, you know, those 3 spots are shaded, and then how many ways can all 7 cars be packed in the lot? Obviously, car is different. Also, the parking spot is different. It's a permutation problem. So we want to have the end result of like, you know, who is in which. And basically 6 teachers are different teacher, and the principal is also different. So basically, you know, each spot has different number. So what we do is that since, you know, when doing that type of permutation problem, always start from the most restrictive. And obviously, the principal is most restrictive. He only can park in 7, 8, 9. So basically, you know, we can arrange to park the principal first. Otherwise, if we park the teacher, and teacher may happen to like the shaded spot too, and they could squeeze the teacher or squeeze the principal out of his position. So basically, you know, it's better to park principal first. So principal has 3 spots. So basically that's 3. Then the remaining, for remaining teacher, so basically the step we are building, is that, you know, people oriented. So the people, sometimes you can so the principal first, that's 3, then the teacher 1 like has 8 spot to choose from. Any of the remaining, for example, teacher parks there, so he has 8. Then the teacher 2 has 7. So basically it goes down. So in fact, you have 8 remaining spot to park the remaining 6 teacher. So it's 8 permute 6. So equal to 8 multiply 7 multiply 6 multiply 5 multiply 4 multiply 3. 1, 2, 3, 4, 5, 6. So this is 8 permute 6 is also equal to like 8 to the 6 following factorial. Following factorial means that, you know, each number you minus 1. So basically, you know, this is just 2 different symbol for this action. And this is how teacher arranged. Then you also multiply by the leading 3. Leading 3 is the teacher. So basically it's 3 multiply this. That's going to be the end result. It's a quite big number. So basically, you know, but anyway, this is how you should do it. And then let's try to do this problem. And this problem is that how many distinct triangle can be traced along the lines in the diagram below. So triangle, obviously, we have to go 3 sides. And obviously, and if we pick all 3 sides passing through the same, this is the coincide place point. So we have 2 points, have more than 2 lines coincide. So basically, if I choose 3 lines coincide at this point, it won't make a triangle. So basically, all the line passing through either A and B. And so basically, the only way to make a triangle is that, 2 lines will pass through A and 1 line pass through B, or 1 line pass through A, 2 lines pass through B. That's the only possibility. And so given this fact, we actually have several different ways of doing it. One way is that, I can, if in this arrangement, I can choose any 2 lines. There are 1, 2, 3, 4, 5. These are 5 lines passing through A. So I can choose any line, 5, choose 2. And then multiply. This is also 1, 2, 3, 4, 5. 5, choose 1. So this is the triangle that passing through. For example, I pick those 2 lines, and then I pick this line, then actually make a triangle look like this. And so it's a legit triangle. So if I multiply this basically is 5 multiply 4 and 2 multiply 1 multiply 5 divided by 1 factorial, just 1. So this is 2. And this is like 10 multiply 5 is 50. So 50 in this arrangement. And this is symmetric, so there's also 50, so it's 100. So that's the way that you can do it. And so basically, I think it's also may be possible that if you use a different way, you can also do it. So you can choose any 3 lines, including those coincide line. So basically, if I choose any line out of 10 line, that's 10 choose 3. So that includes those illegit line. Those are disqualified line. So right now we need to minus the disqualified line, which will not make a triangle. And which other lines not disqualified is that if all 3 lines pass through A, then it's disqualified. Or if the line all pass 3 line all pass through B, it's also disqualified. So to find all the 3 line combination pass through A, it's just 5 lines choose 3. And so does the B. So 5 choose 3. So this is like 10 multiply 9 multiply 8 and 3 multiply 2 multiply 1. So basically we can cancel this out. This is 3 and this is 4. And this is 120, so equal 120. And minus, this is going to be like, so we know that in the combination like 5, 3 equals 5, 2. It is the combination identity. So 5, 2 is just 10 because we already calculated. Yeah, 5, 2 is just 10. So it's 5 multiply 4 divided by 2 multiply 1. And so basically it's just 10. So minus 10 and minus 10. So if I minus 10 and minus 10, I'm going to get 100 also. So basically there are two ways to solve this problem. And let's try to, I think it messed up. Let me close it and open it again. So this problem is that regular dodecahedron has 12 pentagonal faces, 20 vertices, and 30 edges. How many of the triangles which can be formed by connecting 3 of its vertex, at least one side within the dodecahedron? So basically, I have 20 vertices, and in order to make triangle, all I need to is just pick 3. And so basically I can pick this like 3. It's going to form a triangle. And I can also pick this, and this. It's also going to be forming a triangle. So these are all legit triangles that at least has one side within the dodecahedron or dodecahedron. Then, but if we pick 3 points, for example, 1, 2, 3, and here it's not legit. It's not satisfying the at least one side within the dodecahedron. So we kind of just, still using the combination, because we know that none of the two vertex is collinear, because we cannot find, a straight line which connecting 3 of the vertices in this dodecahedron. So basically, any 3 point will make a legit triangle, just triangle, not talking about, within triangle. So that's 20 true 3 is going to be the big number without any restriction. Then, we're going to take away the disqualify the illegit one. In the illegit one is the ones that have 3 points on the same face. So each face has 5 points. And so I need to choose 3 points, 3 out of this 5. So 5, 3. And I have 12 faces. So basically these are all the total of illegit triangles, which is including this total. So if we do this calculation, I should get the right number. So 20 multiply 19 multiply 18 divided by 3 multiply 2 multiply 1, I can cancel this out to be 3, because 3 multiply 6 equal to 18. And then I'm going to minus this. This is basically, equal to 5 choose 2. 5 choose 2 is 10. And 10 multiply 12 is 120. So basically that's the number. Here we just do some calculation. It's 19 multiply 60. And minus 100. So that's going to be 1020. 1020 going to be the answer. And then let's try to do this problem. That just speak up if you feel confused, or if you have questions, because I want all of you really understand it. And this is another question. This possibly is the most difficult out of this batch. And let me keep doing this first. I'll leave the most difficult one to the last. And an octahedron die That's 8 face with sides numbered 1 through 8 row twice, and the product of 2 rows are computed. How many different rows produce a product that is composite? So like 2 dice row, usually it's easiest by just doing a matrix because 8 dice is a small number. So let's say the colon is the row 1, and this is the rows representing the row 1, the colon represent row 2. So we can actually, make a table or matrix by this. This is 1, 2, 3, 4, 5, and 6, 7, 8. And so we can do this very easily. 1, 2, 3, 4, 5, 6, 7, 8. And so obviously, try to find all the composite. It's actually maybe taking more effort. So basically, obviously, like 2 multiply 2, 2 and 2 is going to get a composite. But it may be easy to just take away the prime. And also 1 is special. 1 multiply 1, if you roll, the first row is 1, the second row is 1, it's not composite. So 1, 1 is not composite. And the 1, 2 obviously is not because it's a prime. So 1, 2 is not, and 1, 3 is not. So basically, we're going to color it with a, these are not. Then 1, 5 is not, 1, 7 is not. Then in this direction, it also this way. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 of those are not. So 9 non-composite. Others are all composite because, if it is one of, if none of the multiplier are greater, if all of the multiplier are greater than 1, it must be a composite. So anything from here will be composite. Then plus those number already composite. So basically, I finding this way is easier. So basically, it's actually 64 just minus 9, going to be 55. Obviously, there's another way you can do it, is that obviously, if you draw this diagram, you find that, those 7 colon from 2 to 8, for those 7 colons, 7 multiply 7 equal 49. For those grid, they must be composite. Then we can adding the extra composite on each side. So this is 1, this is 1, this is the other one. It's symmetric. So basically, if you 49 plus 6, still going to be 55. So that's the easiest way doing it. And let's try to do this problem. And 5 lines are drawn so that each intersect the other 4. So 5 lines, so that actually sounds more like a star. So if you have a star, basically it's the edge of the pentagon. It's not necessarily regular, but it's a pentagon that if you extend it, it's going to intersect. So basically, each intersect the other 4. For example, this is a line. Let me label this line to be yellow. So for example, this yellow line intersect line 1 and line 2. So one intersection, two intersection, three intersection, four intersection. So this picture actually works. And so that, oh, and but no three line intersect at the same point. All this means is that non-three lines are coincide on the same intersection. So this is a legit picture. Each of the point of the intersection is then connect to every other point of the intersection. For example, this intersection going to be connect with intersection, and this intersection also going to be connect with this intersection. So basically, how many triangles are formed which have three of the point of the intersection as the vertices. So basically, four line or five line. So five lines. This is line 1, 2, 3, 4, and 5. Five line intersect with all other lines. It will produce 10 intersection because it's actually the number of the intersection it's going to be produced is actually 5 choose 2 because any two line will produce a intersection if this do not happen, if the coincide on one point do not happen. So it's 5 choose 2. So the first step is find the number of the intersection by 5 line, and that's equal to 10. And we can verify it by doing a pentagonal star. Pentagonal star, you have an inner layer of the 5, you have outer layer of the 5 intersection. So that's 10. And how many? So if we pick, then the next step is actually pick any 3 point out of those 10 intersection produced. So basically it's 10 choose 3 equal to 10 multiply 9 multiply 8, 3 multiply 2 multiply 1. And we can do the this. So basically it's actually 120. So how many triangle could be formed? That's 120. And then let's also do this problem. This problem is a mouse is placed as shown in the maze below. If mouse only move up or right, so this is going right, this is going up, and that's only allowed to move. How many different paths can the mouse use to take to get a cheese at the end of the maze? So cheese is here, mouse is here, and the mouse need to make 1, 2, 3, 4, 4 step right, and need to make 3 step up in order to get to the cheese. So basically it's equivalent to make a letter out of, make a word out of 7 letters. 4 of them are right, are, 3 of them are U. So basically 7 factorial divided by 4 factorial and 3 factorial. So that's going to be, it's also equal to 7 choose 4 or 7 choose 3 because you are choosing the 7 or 3 step going up. And it's actually equal to 7 multiply 6 multiply 5 divided by 3, 2, 1. And there's going to be 35 ways that you can do it. And so just for the completeness, You can also using label method. Label method is that from this intersection, you have one way to reach the cheese. From here, you have one way, so that's 1, 1. And then here, you can make two way. You can make one way still here, 3, and 1, 4, and 1. And this is 1 plus 2 equal to 3. And 3 plus 3 equal to 6. And 4 plus 6 equal to 10. And this is going to be 1. 1 plus 3 equal to 4. 4 plus 6 equal to 10 here. And 10 plus 10 here equals 20. And this is still 1. And this is still 1. And this is going to be, oh, that's, sorry, this is not 1. This is still 1. This is 1 plus 4 equal to 5. And this is 5 plus 10 equals 15. And 15 plus 20 equals 35. So basically, if you just use the path labeling method, you're going to get exactly the same result. Okay, let's tackle that most difficult problem. So this one is a standard checkerboard, has 64 squares alternating black and red on an 8x8 grid. So this is a checkerboard. And how many of the 1,296 rectangles on the checkerboard contains more than one red square? So basically, first we have to figure out how this number come about. Basically, we are trying to make rectangle by choosing 2 horizontal side and 2 vertical side. So horizontal line along the grid, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 possible horizontal line to choose those 2 horizontal one to make a rectangle. Vertically, it's the same. So basically, it's 9 choose 2 multiply 9 choose 2. And that's going to multiply up to 1,296. So that's the total rectangles. Rectangle obviously including square as special case. And we can try to multiply it. A multiply 9 divided by 2 multiply 1. And this is 4. And that's 36. And this is just 36 square. And if you calculate 36 square, it's exactly 1,296. And so this actually, just by understanding how this number comes from, shed light on what you can do next. Obviously, contains more than one red square. So contains more means that it has to contain at least 2 red square or more. For example, this is a legit one. And this one is not legit. Obviously, it just contains 1. And this one is not legit because it contains 0 red square. And this one, it's not legit because it's contains just 1. Or this one is not legit. It's contains just 1. And then this one is not legit because it's contain only 1 square. And so does this one not legit. Then for all the rest, it's actually legit because, I can 2 by 2 is, and even 1 by 3 could be legit if I include 2 of the red one here. So basically, we just have to figure out how to calculate exclude unlegit one. It's very hard to calculate all the legit one because you can have bigger square, a lot of those. And so we're trying to exclude those. This is the exclusion, those are exclusion, those are exclusion, exclusion, exclusion. So obviously, those exclusion is the easiest one. Just contain one square, either red or black. There are 64 of those. So basically, this number need to minus 64. 64 basically. Then we trying to exclude those ones. So let's say try to exclude the vertical ones. Vertical one, basically, we can do the vertical one. This is the first one, and this is the second one, and this is the third one. We can just draw along it. And so basically, this is the first one. And all the way to the last one is here. So basically, there are 7 of those. Because if we check just starting position of this, two grid rectangle, the first start from the last legit one start position 7. So basically 7 of those. 7 of those, and we have 8 colon. So each colon contains 7 little rectangle. We have 8 colons, so it's 8 multiplied 7 for those type. And for this type, it's actually symmetric. That's 8 multiplied 7. Then horizontal one, it's actually 7 multiplied 8. Because horizontally, I can find each horizontally, I can find each horizontal line, I can find 7 of those. Then I have a total of 8 rows, so 7 multiply 8. So basically multiply on minus 56, minus 56. Then I'm trying to find those ones. And for the black one, obviously, the first row, I have, this is the first one, and the second one has to start from here, span here, and this is the third one. So for each row, I have three of those. I have 8 row horizontal ones. So that's 3 multiply 8. 3 multiply 8 is for those type. And then for the vertical one looks like this. If I label it, I can draw one here. Then the second one is here. The third one is here. So for each colon, I find 3 of those. And I have 8 colon. So still 3.8, so multiply 8. And those are 2 different type, minus 24 minus 24. That will get the whole count. And I think we'll leave the calculation. I know the method is right, so that's the way you do it. Does that make sense for those problems?
Yes.
Okay, thank you. And so basically, counting is actually a very tricky thing. And complementary counting is actually a very important concept we have to master. And it's all about like the Venn diagram thing. And so basically, especially, it's a 2 category thing. It's actually most used actually is just 1 category. And like A plus A complement equal to the whole set. S means the whole sample set you're trying to calculate. And then, for example, this is the flip a fair coin 8 times. In how many ways he can flip at least 2 heads. And so let's review a little bit on last time's class. The last time's class, we have been talking about the combination, and combination is a very is actually a very important concept, and it's unordered arrangement. And the unordered arrangement especially is useful in terms of the in terms of coin flipping, and also in terms of the binomial. Actually, you know, like this this type of the writing, like 8 choose 3 or 8 choose 2, a lot of places say it's just binomial coefficient sign, basically. You know, it is just, you know, binomial coefficient. And since we are talking about this, I think let me deal with the Pascal's triangle first, because Pascal's triangle will cover this problem. Otherwise, if I don't cover the Pascal's triangle, we actually don't show the background for this. So the Pascal's triangle, and Pascal is a very famous guy. And actually, you know, if you do the probability and the statistics, Pascal is one of the original, like, you know, inventor of the whole subject, and together with Fermat. And or the whole subject start as they kind of began to communicate with each other, like with long letter, and they write each other letter, and those letters still preserved, and you can even search the image of those letter, and it's just like a message we are using right now. It's amazing they still keep it. And so basically, Pascal's triangle is actually, you know, it's a very simple triangle. It's actually used a lot in like elementary school just for practicing the addition. And the first one is, so this is one all the way, and this is one also all the way. Then you kind of just adding together 1 plus 1 equal to 1 plus 2 equal to 3. And then you kind of will just go down this way, and especially you are able to construct the whole triangle very quickly. And one of the phenomena you have is that the total sum, if I sum the number horizontally, then the first row is 1. 1 is also 2 to the 0th power. And this 1 plus 1 equals 2, 2. 2 is to the first power. And if you add it, it's going to be 2 to the second power, 2 to the third power. And whatever row, it's also 2 to the nth power. So that's kind of the special feature about the Pascal triangle. And the Pascal triangle also, if you are counting the pass, so right in the last problem, we actually doing the pass counting. For example, let's say that mouse start from here. This is the mouse, and this is the cheese. We can also label this grid, and we can get this. And here is 252. And if you check those lines diagonally, you will see that this is the Pascal number 1, 1, all the way 1. And this is, so Pascal number appear here also. And Pascal number actually come up in the coin flipping too. So let's say that the example is that fair coin is flipped 7 times. How many outcomes show 0 tail, 1 tail, 2 tail, all the way to 7 tails? And actually the way is that, you know, the 7 ways, it's just bigger. You know, it's actually will be exactly the same as these. So let's try to use the coin analogy. And we know that flip just one coin, you have head and tail. So that's the sample space. In statistics, in probability, we call sampling, experimenting, and the result of each experiment. And then if you have 2 coins, the result set looks like this: head, 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 tail, and tail, head, and head, tail. And we look like we know that it's going to be 2 to the nth power. Why? Because you can use a tree diagram. So basically, starting from this, the end result is each flip. So one flip, it's a 2-branch tree. That's the result is head tail, and head tail. That is the complete set. And then if you have 2 coin flipping, this is the first flip, this is a 2 flip. Second coin flip, if your first coin flip to be head, then after flipping head, you still can flip head and you can also flip tail. And the result set is symmetric here, head, tail. So basically, you know, this is the result of the, and I'm going to write the previous result, concatenate upon it, because that's going to represent the complete final set. So this will construct the second layer and the third layer. You can keep building this. Adding one more coin, your result set, your sample result set will be multiplied by 2. So basically, you know, the coin flipping, the end result is 2 to the 7th. And 2 to the 7th, then just by looking at it, you know, if I do 3, then if I keep building this tree, I will like head, 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 tail, and head, tail, head, head, tail, tail, then tail, head, head, tail, head, tail, 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 head, and the tail, tail, tail. So basically, you know, this is the complete result space for the 3 coin flip. So basically, you will see that, you know, in order for this is the 0 tail, and the 1 tail, basically you come up here, and so basically, in the tail, why it is so starting from 3, it's became very obvious. To get 1 tail, it's just matter of choose the tail position. The tail appearing in the first position, tail appearing in the second position, tail appearing in the third position. It's actually, because we have 3 positions, it's just we choose 1. So basically starting from 3, and then the coefficient, or the, like, we can flip 2 tail. Flip 2 tail is just we are choosing the tail, two tail position out of three, a total of three positions. So this is its place. This is its place. So basically, it's 3 choose 2. So basically, the coin flipping for each case, you have to understand it this way. So basically, this is how you flip coin, how the binary tree goes up, like so that vertically, if you seeing it, it's always 2 to the nth power on the summation of the all the result. And for each possible number of the coin, it's always a combination because it's all about picking the tail letter position out of the total of the n coin. For example, if you flip 3 coin, then head, 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 because it has no tail. So basically, it's just choose 3, choose 0. And then if you have one tail, it's 3, choose 1. And then it's 3, choose 2, and 3, choose 3. So this is just the way that it was arranged. And it's actually quite intuitive. It's not that counterintuitive. In statistical and probability, there are a lot of things that are very confusing, very anti-intuitive, and this one is very intuitive actually. So basically, we come with the binomial theorem. Binomial theorem is absolutely one of the most important thing in the probability and the statistics. You just have to remember it. So binomial theorem is actually, you can have analogy and similarity. You can link this, the binomial expansion, with the coin flip and link a one-to-one relationship. Let me show you how. So basically, this is X and Y, and you can link X with head and Y with tail. So basically, and each one when you multiply, because when you multiply, two binomial, basically, it's just FOIL. First, outer, inner, last. And so binomial, each term, starting from binomial, each factor has 2 term. And so the number of the final term without combination, before you combine them, before you combine the like term, the terms it will produce is 2 to the nth power because of the multiplication rule. This is 2 multiply 2 multiply 2 multiply 2 multiply 2. And each term you produced has a combined exponent or a combined index to be 5, because no matter which term you pick, you will increase the power by 1. So basically, after the multiplication, basically the result is like a coin flip. It's exactly like coin flip. The coin flip will have a head tail letter sequence. And then when you multiply it out, it's going to have a XY sequence. If you put the order exactly, don't try to change it. So basically, before you do anything fancy, it's exactly the same as a coin flip. So basically, but like term could be combined. So you don't care about this is X, X, Y, 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 or you care about X, Y, 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 X. So basically those terms are the same because those could be combined. Those are all X squared and Y cubed. So basically, how many turns do you have? Because you're actually rotating through the whole possibility. It's just like, like within 5, how many ways to choose 2x position, the remaining will be by. So basically the coefficient for this turn is actually 5 choose 2. So basically, this is so that's why also the choose function is also sometimes called like binomial coefficient function. And so when you expand it, the result will be actually x plus y to the nth will be n choose 0. So basically, let's say that, uh, y is the tail. So this is the 0 tail. This is all head or 0 tail situations. And this is 1 tail. So basically all the way to all tail. So basically, this is a fairly intuitive. And you actually could, this is the binomial theorem. Actually, a lot of times they also do the summation in the like simplified format. It's like, like x plus y to the nth equals to like n equal to 0 all the way to n. And this is, let's say I equals I from 0 and n choose I and x to the n minus I and y to the I. So basically this is the, sometimes you will see it in this format. But anyway, this is all like, binomial theorem result. And so basically we actually link them together. Also, there's a very important fact. So basically, the Pascal's triangle we could write in this format. So this is, we replace 1, 1, 1, 1, 2, 1 with the binomial coefficient. It's actually exactly this pyramid. So start from 0, 0, and the way to, so 0, 0, it has to be 1. It actually is 1. 0 choose 0. To choose 0 item out of 0 is one way. You have one way to do that. And then you choose 0 item out of 1. This is one way. 1 item out of 1 is also one way. And then, but you actually in the statistic you can also have like 1 through 3. 1 through 3 actually equal to 0 for if the bottom number is bigger than the top number, then the way to choose is 0. And if the bottom and top number are the same, it's 1, then above that it's much more intuitive. And this is a little bit abstract because choose 0 item out of 0 sample sets, that's really kind of confusing, but this is just the way it was defined. Then the whole structure could be constructed. And so there's one thing that, one thing out of this Pascal's triangle is that it's a very famous or Pascal's identity. So this Pascal's identity, you also have to remember it. And so Pascal's identity, I always write it in this way. So there's one side, you can follow me. I recommend you to follow me writing it so you will remember it. So basically, let's write together. So you do like this is like n and k. N choose k equals, then we have add. So we write out the framework. So on the far side is just everything minus one. So basically n minus one and the k minus one. And on the close side basically it will share the, so it's actually, this is the two item side. This is the one item side. And two item side will share the top. So the top will be the same, n minus one. Then the one item side will share the bottom number with this. So this is k. So basically this is the way you construct the Pascal's identity. Pascal's identity, for example, you can like, for example, if you can do a real number. For example, 100 choose like 9 equals, you can say, you can write out very quickly both number reduced by 1, so that's 99 choose 8. Then the top will be the same, so 99, and the bottom will be the same, so that's choose 9. So basically 100 choose 9 equals 99 choose 9 plus 99 choose 8. So this is actually, because here, if you construct a Pascal's triangle, this is like, 3 choose 1, 3 choose 1 is actually equal to, so you actually can add here is actually everything minus 1, 2, 3, 3 minus 1 equal 2, 1 minus 1 equals 0, and here share the top, that's 2, and share the bottom is 1. So basically, here you actually, is able to decompose 3 choose 1 into 2 choose 1 plus 2 choose 0. So basically, the whole thing. So let's do a summary. What's the Pascal's triangle? So the first thing is Pascal's triangle. Actually, if you just write numerically, it starts from 1, and diagonally, you always inherit 1 on both sides. And in the middle item, you just add them up to construct 2. So if you keep doing the middle item is, a summation of diagonally related top 2 items, and then each layer will add a, head 1 and the tail 1, then you will be able to construct this Pascal triangle very easily. It's just like a low grade elementary school, like, adding practice. But the magic thing about it is that each layer is actually 2 to the nth power. The first row is 0. Your first row is 0. It do not start from 1. So it's actually 2 to the 0. And so basically, the summation of all the binomial. So right now, the Pascal, because it's actually directly related to, binomial coefficient. So actually, truth function is also called binomial coefficient function. And it's heavily related to the coin flipping. And basically, it's the same thing as the coin flipping, or also same thing as the path finding. So it appears so many places magically. So that's a very interesting and very fun fact. And also, given that all the middle number could be back traced to the summation of diagonally related to top number, we have this Pascal's identity. And this identity actually could be proved. I don't have that much time to prove it, so basically I will skip that. But I recommend you to go to the Wikipedia and look for Pascal's identity. And it has like 3 or 4 different proof. And it's very interesting. But just for testing or computation purpose, let me write out this Pascal's identity again. First, you pick any two number. It could be like right now is nk. You can like n plus 100 and k minus 3. So basically, this is far side, this is the close side. So the far side will be both top and bottom reduced 1 by 1. So n plus 99. And the bottom is k minus 4. And top will be the same. So this will share the top. And n plus 99. And the one side will share the bottom. So basically, that's going to be the k minus 3. So basically, that will construct the Pascal's identity in any situation. And why is that true? Because it's true because, you know, intuitively speaking, it's just how the rule, how you construct the Pascal's triangle. Every middle term is a summation of the diagonally related to top layer term. Okay, so we kind of get enough of the Pascal's triangle. We have the knowledge to tackle this problem. And yeah, so what we know is that flip a fair coin 8 times, the total possibility is 2 to the 8th. That's obvious because it's the summation of, you know, it's just 2 to the 8th. If you construct that by the tree diagram. And how many flip? At least 2 head. At least 2 head, we had to exclude that 0 head and 1 head. 0 head is basically it's all tail. All tail has only 1, so basically it's 1. And so it's C, it's 8 through 0. 8 through 0, basically, you know, you can also write it this way, especially if you write on computer. And this is actually a preferred way because it's much easier than this way. And if you write on the paper, you write this way. And then the way to have 1 head is just 8 choose 1. So basically, you know, 2 to the 8th minus 1 minus 8, that's going to get you to the at least 2 head. So that's a complementary counting. Complementary counting is just a counting that, you know, if you have something with certain property, it's a subset of the full sampling space, then it's complementary. And A plus A complementary is always equal to S. So that is actually, you know, a very obvious fact. And so a lot of time, you know, if you're trying to summation those, that's possible, but it's much more cumbersome than doing this way. Okay, so let's do this problem. And Corey and Tony are friends on the same basketball team. There are 8 players on the team. How many starting lineup of 5 players include Corey, Tony, both? So basically, first we trying to find out, you know, how to pick 5 players out of 8 without any restriction. That's 8, choose 5. And then because we including Corey, Tony, or both, then that actually, we can also calculate that, but it's actually more difficult to calculate than we just find the lineup without both. Without both, then basically we have a smaller pool of the player to choose from. We only have 6 players to choose from. So we 6 choose 5. So 6 choose 5 and 8 choose 5 is equal to 8 choose 3 and 6 choose 5 equal to 6 choose 1. So basically that's actually, you know, will be this way. And 8 choose 3 is 8, 7, 6 multiply 3 to 1. So this cancels. And 7 multiply 8, 56. Minus 6 choose 1 is just 6, so equal to 50. So this is the way that you're going to complete this type of the calculation. And actually, it's also possible to like do it building up. So we can do it this way. Let's say that, you know, how many line up of 5 players, including Corey, Tony, or both. Let's say that including both. Let's say including both, basically, you know, we have position 1 and position 2 is already Tony and Corey. Then we have remaining, we have 8 player, and 8 player need to choose 3. Remaining, we have 6 player. So we have to 6 choose 3. So basically that's the first situation. Then another situation is that, you know, so this is a situation relatively easy to manage. Then 5 players, including Corey. If we only including Corey, and so let's say Corey is already selected, then we need to select 4 person. So that's the 4 person. But the remaining people, we cannot select Tony. So basically, the remaining is not 7. The remaining is 6. So we have to select remaining 4 player from the 6. And this is symmetric. This also works with Tony. So if we already select Tony and we refuse to select Corey, and it's also, so it's 2 multiply this. So 6 choose 4 equal to 6 choose 2. So basically 6, 2. And then plus 6 choose 3. So basically, you know, if we are doing this type of the work, supposedly we'll come up with the same result. So 6 multiply 5 multiply 4 and 3 multiply 2 multiply 1. We cancel this out. And this is 6 choose 2 is just 6 multiply 5 divide by 2. And this is going to be, also we're going to multiply 2. So I think I'm not going to cancel this one, just cancel that 2 outside 2. So this is 30. So this is 20 plus 30, still going to be 50. So basically, you know, a lot of problems, especially the simple problem, you actually have a multiple paths. Just don't be afraid of doing anyway. And it's actually, you know, just do it confidently and it should work out. Let me see. It frozen again. So let's do this problem. The 54-member Council for Security and Cooperation in Europe wishes to choose 3 member states for different leadership positions. The lobby decree that at least one of the Lithuania, Liechtenstein, Latvia, and Luxembourg must be chosen. In how many ways can the committee be selected? So basically, this type of the problem, especially you look at those, how big the number is that, you cannot even try to grapple it. So you basically 50 so first we choose, like we do the 54 without restriction. 54 choose 3 member and for different leadership roles. So they are different. So it's a permutation. The different means that, the order matters. So it's for 54 permute 3. And so at least one of them chosen. That's actually, could be, there are so many cases. Could be this being chosen, this being chosen, this being chosen, or 2 of them being chosen, or 3 of them being chosen. There are so many cases. It's just very hard to do. So the way to do this problem is that, how about counting, try to exclude none of those countries being chosen. None of those being the country being chosen, we have 4 countries, 4 European country, and we minus the 4 from this 54. So basically, if we do like 54 permute, 50 permute 3, that's going to be, these are fairly big number, and so I'm not going to calculate here, but this is just a way that I'm feeling that this is not a really super good example, especially the second one, because I can do it either way. It didn't really necessary, you have to do it this way. But, this is a better example because you have to do it this way. If you do the other way, it's going to be go through hell. Yeah. And yeah, this is another example. I think let me just do more problem, and I need to finish this part. So basically, because this class we go through a lot of example. We also go through Pascal's triangle, explain very clearly, also show the Pascal's identity. So we're going to finish this class on the stick and stone. I don't have time to cover more examples, and we'll just go here. And so the stick and stone, sometimes you are dealing with even more difficult problems. So basically, stick and stone problem, you have to observe the pattern. Usually these type of problem are the ones that you cannot even enumerate through casework. So how does that work out? So this is one of the example, is that Uncle Henry has 10 $1 bill to distribute among his 5 youngest nieces and nephews. How many ways are there to distribute his money? So basically, if you really do the reasoning, how much money, how many ways you can distribute, it just goes through the hell, because you can give all the money to one child. So basically, that's $10 goes to all the lucky one. Then gave $2. Every person gets $2. So that's basically one way. And then you can give $0, $1, $2, $3, and $4, $5. This is a 5 factorial way, really. Then you can give like a $0, $0, $2, $2, like then $6. That's also so many different ways. So basically, it's just unmeasurable ways that you can distribute. So then we kind of settle down that we actually find out that, the dollar, each dollar bill, each $1 bill, it's just like a rock. And those are identical thing. And how about I use 4 bar? And why 4 bar? Because I have 5 nephews and nieces. And those 5 bar or those 4 bar basically, create 5 space. So 4 separator. 4 separators create 5 space. Those 5 spaces each stand for one of the nieces and nephews. For example, this is 1, 2, 0, 1, 2, 3, 4, and 5. So basically, the first 4 do not receive a single dollar. And obviously, the 5th one, maybe the youngest one, maybe he is so cute that, earned the heart of this uncle. And so he bestowed all $10 upon this lucky one. And okay, so this one is like, this situation is like, this is the niece and nephew 1, 2, 3, 4, and 5. Obviously, the fourth niece may be a like naughty one and show disrespect. And the 5th one may be the cutest one. And then the others one are so-so. And so they kind of so this kind of distribution. But anyway, there's think about artificial bar. These are the artificial introduced separator. Basically, because you have to distribute $10 anyway. So basically, the way to create their different distribution is just use separator to divide between the $10 to create all the possible distribution. And this actually will be a complete possible list of distribution. And it's unlike the first reasoning that you have to enumerate so many of those. And in the end, you still could be missing some. And this will include all. So basically, if we treat this as a ladder arrangement, so basically, you can treat this as like each bar 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you have 10 bills and plus 4 separator. Then it's equivalent to a 14 letter word arrangement, and with 10 of them duplicating and 4 of them also duplicating. So it's actually, just is actually, 14 factorial divided by 10 factorial and divided by 4 factorial. So basically, 14 factorial is assuming all those letters are different. Then we divide by 10 factorial, that's 10 factorial of multiplicity. And then also divide by 4 factorial of multiplicity. That's 10 factorial multiplicity is $40. 4 factorial for multiplicity is for the separator. So basically that's actually is our trick. And this has been used very extensively in the test and is very, very, very important, super important. So it's actually, since this arrangement is also 14 choose 4. So basically it's just, out of the 14 positions, and how do I choose 4 separators? How do I position? So this is another example that place Yeah, stick and stone is place divider sticks to separate indistinguishable items, stones, into categories. So basically, in here, the dollar bills are totally indistinguishable. And the categories, niece and nephews, those are distinguishable. Those are different person. So, um, so this is another example is that you are ordering a half dozen donuts and need to choose from among four flavors: glazed, powdered, cream filled, and jelly filled. How many different donuts orders are possible? So this is still the same. Basically, the donuts could be of different flavor. And we have four different flavors. So basically, that's four category. So the number of the stick is always one less than the category. And so we have 3 stick and we have 4 donuts. So that's 3 plus 6 equals to 9. And then it's the 9 through 3. And this is basically equivalent of finding the letter arrangement. So sometimes we are dealing with stick and stones with restriction. And for this example, it's asking how many ways are there to roll a sum of 7 with 3 standard 6-face dices. And roll a sum of 7 with 3 face dice. Basically, we know that each dice start from 1 all the way to 6. So 1 all the way to 6, 1 all the way to 6. So basically, it's actually quite hard to list. So basically, we can do this casework. You still can figure it out. Basically, if you do like 5, 1, 1, basically one of the dice rolls 5, the remaining 2 rolls 1. You actually have 3 ways of doing it because you can, the first dice roll 5, second and third both roll 1, then you can rotate it around. The first roll 1, second roll 5, the third roll 1, then the first 2 roll 1, the third roll 5. So that's the 3 way for this. Then you can also have like 4 to 1. And 4 to 1, basically you have 6 ways. So basically, and then 3 to 2, you have 3 ways, and 3 3 1, you also have 3 ways. So you actually have 15 ways. So basically, that's enumerating. That's enumerating actually is way less convenient than trying to divide the place into 7 dots. So this is 1, 2, 3, 4, 5, 6, 7. So we have 7 dots. And the 7 dot, and we have 2 spacer to point. And this time, basically we are finding the gap because this is gap 1, because Because remember, this case is totally different from the previous case. The previous case, basically 3 bar could be adjacent. This, for example, for this case, it's there are 4 flavor. The first is glazed, the second is powdered, the third is cream filled, the fourth one is jelly filled. So basically, if I label it this way, this is just, I buy all 6 donuts jelly filled. And this basically, rolling dice is totally different. You have 7 dot, but each dice need to have at least 1 because there's no dice has 0 dot. So basically the way to arrange it is that, uh, we cannot say that 2 plus 6 and choose 2. That's way too many because that's going to include like this situation that, first 2 row do not have any dot and the last row has 7 dot. That's just simply impossible because, neither the 0 will exist or dot 7 will exist. So basically we have to look at different ways. That's why it's stochastic with restriction. So the position, the number of the position we can pick is that we have to insert the bars into the gaps between the dots. So 1, 2, 3, 4, 5, 6. So we have 7 gaps. And 7 gaps, in 7 gaps, we have to place 2 bars. So basically it's just 7 choose 2 or 6 choose 2. 6 choose 2, that's going to be, 15. So that's the way to do it. Let me also, show this in a totally different way so you can really convert this restriction into the original layout. So basically you can think, so one way to think about this restriction is finding the gap between those dot is 6 gaps. You have to put, so for example, if I put in gap 1 and the 2, basically, still it's legit because the first dot means that the first dice roll 1, the second dice roll 1, and the third dice roll 5. So basically, it's a legit one. And so the other way is that if we really convert, so this case is gap and sticking the, let's say that this is sticking gap. Sticking gaps. So this is not stick and rock. Stick and rock, you can have categories with 0. And this basically using the gap, creatively solve this problem. And let me use a different viewing angle to do this. So basically, if we have 7 dots, so basically I can view this problem in a totally different angle. A totally different angle shows this way is that, let's say that I already distribute 1 dot to each of these spots. So basically, I only need to divide 4 dots into 3 categories. So basically, I have 4 rock. And I need to do 3 categories for 3 different rows. So I had 3 categories entitles 2 stick. So if I 4 rock and 2 stick, because the 3 of them is already fixed in the each row 1 and row 2 and row 3, then basically I have less rock to work with. And this 2 stick is allowed to, have doing this. This is just corresponding to add 0. So this 0, add 0 to row 1 is already existing 1 rocks. Add 0 to existing 1. So that's 1, 1. Add 1 to 5. So this is 1, 2. Oh, add 4 to 1. So 1, 1, 5. So basically, 4 rock and 2 stick. So I just minus. So one of the major trick dealing with rock and stone is that if certain spot are guaranteed to have certain value, you just subtract from the total and make less rock and keep the same number of the stick to arrange it. So basically that's 4 plus 6 equals, or 4 plus 2 equal to 6. This converts this into 6. So converting to this. So both thinking, you have to think it right. So basically that will convert to the same thing. Then let's also do this final problem for today. And so each of the number 1 through 10 is placed in a bag and drawn at random with replacement. With replacement means that, if you pick 10, then you still place this 10 back into the bag. The next time you still can draw 10. So how many ways can 3 numbers can be drawn whose sum is 13? So 13 is the number, and then basically 13 basically is like if you view it this way, 13 basically have 12 gap. You have 13 rocks and with 12 back gap. So we are 12 choose 2. 12 choose 2, but we have to exclude. We have to exclude certain situation. Is that because this situation actually do not work because the first one is 1, the last one is 1, and the middle one is 11 because 13 minus 1 equal to 11, and you don't have a number 11 to be drawn. So we have to exclude this. So we have to add minus 3 because this is one layout, this is the second layout, this is the third layout. And so basically this is another with restriction using the gap. But this gap has some problem. So let's think about it in different ways. So basically let's assume that, you already have 1 on each place. So you have 13 dot. And you already allocate 1, at least 1 in those places. Then basically you have 10 to choose from. So if you have 10 rock to allocate with 2 bar, so we just use the minus trick. It's 10 still plus 2. And because we have 2 bar, 2 still going to be 12, choose 2. But we notice that, those situation like 2 bar with the 10, also 1 bar on both sides, and have 10 and 2 bar, 10 rock here and the 2 bar. Those basically adding 10 to existing 1. So this do not work. And this basically, have three situations, because in those cases, two bar is on both end, or one bar is on one end, one bar is on the other end. If you have any bar in the between, it actually breaks the pattern. All the selection is legit. So basically, in both problem, you can think about the problem by either viewing the gap or either viewing the minus the number to do the um, rock piling. And then, yeah. So when you use the minus, then basically you just to add it up. And also, it's just provide a different angle of the views that more similar, looks more familiar, because a lot of people just feel it's very inconvenient to remember their special case. Inserting between the gaps, it's actually much more easy to just convert everything to the first case, that bars could be clustered into same position. And so basically, either way you like, but anyways, this is just, quintessential meaning and usage of stick and stone. And okay, I think that's all for today, and have a nice one, everyone.